Okay, well, good morning, everyone in person and online to the latest installment of the Bureau Seminar Series. Excited today to have Johnny. Michael here has actually asked to introduce Johnny, so I'm gonna let him do that. Just a few quick reminders, announcements. You're here, so Bureau Seminar, Tuesday mornings, 10 a.m., usually in the BR room. Just a couple of reminders, hold Q&A until the end. And we, the host, will help moderate Q&A. If you're online, drop your questions in the chat at any time, no problem. And just also as a reminder, as we come into the end of this semester, there is still a survey that you can find the QR codes on the doors and whatnot, and the halls and the stairwells. If you have suggested speakers, we'd love to hear it. So again, thank you very much. And I'm going to hand it over to Michael to introduce John.
Okay, thank you. Welcome, everybody. And so I want to introduce Jani and just a couple of sentences about the project itself. So Jani is a research assistant professor. She's been here since March of 2023 and has been working on the comparing electricity options IA since then. Jani got her PhD at IIT Bombay in 2012 in energy science and engineering. She has a master's industrial power and automation and a bachelor's in electrical. She was beforehand, she was the department head of electrical electronics at Multi Institute of Technology, and she was an associate. So this project really began during the pandemic, on the front side of the pandemic, through a gift from Tellurian, which is an LNG company, with really the question asking, okay, what does it really take from an environmental standpoint to run an electrical grid? You know, we have a Texas grid. It's very heavy in terms of combustion-based electricity generation. There's a lot of discussion of energy transition to renewables, you know, wind and solar, batteries. And the question ultimately is, well, what is it really going to take in order to transition a grid to have this sort of low carbon emitting electrical source? And when I say to run the grid, I mean all the way from construction of the equipment to deployment. And so that's really what this is about. And with that, take it away.
Thank you, Michael, and sincere gratitude to all who are assembled here to hear what I have to say about comparing electricity options. So I joined this project last year in May as a life cycle analyst, and I'm here to educate you about what CEO is, what are the objectives of comparing electricity options project, what were our objectives when we started the project, where are we now, and what is ahead. So the team is myself, Michael, Rajan, and Shweta. So the motivation behind the project, just to give an overview, we know that the energy demand is increasing yearly. To understand the gravity of the progressive demand in electricity or energy, it's about 1.7% a year. So when we study about different models, energy system models, we can see that there's a huge demand in electricity and energy as a whole, all sorts of energy like heat, chemical, whatever it is. So the advent of electric vehicles, the increase in population, all these things contribute to the increase in demand. So the motivation is we need clean energy, we need affordable energy, we need reliable energy. These three factors are the underlying motivation of the comparing electricity options project. So it is actually a trade-off wherein we have the society's goal of mitigating climate change. That is the first point which I mentioned, that is clean energy. The second one is providing reliable energy, and the third one is affordable energy. Of course, these three things cannot go together in a pack. We should look into trade-offs between these three different characteristics of the particular system. So that was the motivation, how to arrive at a trade-off between the society's goal of achieving these three aspects of energy and providing this to a global community. So our goals, to be specific for the comparing electricity options project, is the first one, that is clean energy, wherein we look into the local and global environmental impacts. That's what the term clean means, the reduction in environmental impacts, and what all contributes to the cleanliness of energy. All the material supply chains which are part of the electricity generating technologies. So we are looking into how the environmental impacts are impacting both in the local phase as well as in the global phase of all the critical material supply chains, because critical materials contribute more to the electricity generating technologies. Then the second part is, as I have told, reliable energy. So we have to compare the environmental trade-offs for the different energy transition scenarios. We have to look for reliability as well as without much compromising the environmental aspects of energy systems. And the last one is affordable energy, which is we are trying to deduce a metric which includes all the costs, including the environmental cost as well as other external costs which affect the system. So there is a term called transmission congestion cost. Hopefully I'll explain it in the coming slides. So this was the motivation of our project. So this project is actually classified into 3 phases. The first one is the clean energy phase, where we tried to do cradle to grave life cycle assessment. Life cycle assessment is a standardized methodology. I have a few slides explaining the methodology in the coming portions. It is a cradle to grave environmental assessment of the different electricity generating options and critical material supply chains. And we are not only looking into GHG emissions or CO2 equivalent, which you are more familiar with. In addition to CO2 equivalent, we are looking into other 16 environmental impact pathways. So that is the first phase where we do life cycle assessment. The second phase is the reliable electricity, where we combine and test different combinations of electricity generating options. And how do we do that? We use standardized electricity dispatch models so that we will ensure highest reliability at the lowest environmental demand. And usually the time horizon is 30 years. And the last one is affordable electricity, where we will be trying to look into the cost of electricity, the final cost that has to be borne by the consumer, considering all the components of cost. Not only the production cost, but also including other costs like integration cost, externality cost, including the environmental cost and other factors. So this is our area of interest, and it's West Texas. And we have selected the area of interest in such a way that the facilities can be moved based on the requirement. It can be moved to any location so that the fuel cycle can be changed, and the transmission and distribution facilities are also affordable. So this is the first phase, which I have already mentioned, which is called life cycle assessment. It is a standardized methodology. In life cycle assessment, the assessment starts from cradle. Cradle actually means the sourcing of the materials from earth and ecosystems to the grave. So cradle means you source the material, then you process it, you manufacture the material, you manufacture the product, the operational impacts as well as the end of life. So this portion, the processing to operations portion, is called the gate portion. And the final phase, which is the end of life phase, is called the grave. In this case, for any energy system, it has a cradle phase where it's sourced. The different materials are sourced. And then it has a gate phase where that product is processed, manufactured, and then it is operating in the energy system. And any product, any energy system has its end of life, which is called the grave. So what we do is, in life cycle assessment, which is a standardized methodology, we start from cradle and we end at the grave, analyzing every different life cycle phases. What are the energy and material inputs of the different life cycle phases? So it's not just operation as we usually think of as in an electric vehicle. So probably just comparing this concept to an electric vehicle. In an electric vehicle, the operational emissions are 0. But in a internal combustion engine vehicle, the operations emissions are there because you use petrol or diesel as its fuel. But when we take the total life cycle of an electric vehicle, you have to consider the source of electricity. And if the electricity is produced from fossil fueled plants, as we take it on a life cycle, we start from the source to the gate, or when the electric vehicle is running, you cannot say that it is green because the source of electricity, of course, contributes to the environmental impact. So that is an example of which we compare the cradle phase and the gate phase of an energy system. This is the methodology where you have inputs, the raw material inputs are coming in, the energy is coming in, and this is the process where you have the raw materials are acquired, it's manufactured, it's used, or it's maintained, or it's operated, and you have the final end of life. And the output is the main product. And of course, together with the main product, you will have byproducts also. And in this process, you'll be having the atmospheric emissions and the land and water emissions. So as already mentioned, we look into a standardized approach, which is the ISO 14040, the Principles and Framework 2006, and ISO 14044, which shows the requirement and guidelines. So whatever we do is based on a standardized methodology. So we are all concerned about greenhouse gas emissions or CO2 equivalent emissions, which is always the talk of the day. But in life cycle analysis, which is a standardized methodology, we look not only into greenhouse gas emissions, we study and understand other 16 environmental impacts which are specified by recipe midpoint H. So we use an open source software which is called OpenLCA, which has a methodology by which we arrive at the results based on a functional unit. So these are some of the impact categories which we consider for our study. Another major one is water consumption, which is expressed in terms of meter cubed of water. GHG emissions, which we all know. Land use, which is how much crop equivalent land is used for the is used in the energy system, starting from the cradle to the grave. You have acidification, you have eutrophication, you have ecotoxicity, and other biodiversity and ecosystem services, which are impacting due to the existence of that energy system. So why do we do life cycle assessment? It is actually easy to just understand the greenhouse gas emissions and note or just present it as this much amount of GHG emissions is there when a particular system operates. So as I mentioned, in the case of an electric vehicle, it's zero, because we assume that it's operating from electricity. But in this case, when we do life cycle assessment, we have to study the entire 16 environmental impacts of all the electricity generating technologies which are under consideration. So as I have already mentioned, critical materials, example, cobalt, nickel, and lithium, and the electricity generating technologies, they are integral parts of the society, and they help us to understand. So as I have already given a description about what is LCA. So it helps us to understand the environmental impacts of the supply chain. Then it helps us to understand the geography of impacts. What do you mean by geography of impacts? You can have local impacts and you can have global impacts. What is the difference between local and global impacts? If the environmental impacts are local and it impacts only a small circle of people, or if it's localized, then it is a local impact. So mentioning the impact category, referring to the impact categories, which I just mentioned a slide back, we can say that water consumption is a local impact because it impacts only the people residing in that area. While greenhouse gas emissions, we all know, is a global impact. It impacts the entire community. So that is the difference between local and global impacts. And that is what we specify by saying geography of impacts. And the cost to build and run the electric grid. Cost means it's not the actual financial cost. Here we are mentioning here we are referring to the environmental cost. How much does it cost you when you want to run the electrical grid? Then, as I have already mentioned, most of the studies focus only on GHG emissions. So we include other 15 environmental categories also. And yeah, so why do we do this? That is the question, or that is the title of the slide. We want to know how it impacts the community. And as I have already mentioned, our first title was clean energy. How can we, unless we understand how the environmental impacts are, both on the local and global basis, we cannot do something to improve the condition. In this case, we have to identify, we have to study how a particular energy system is operated and how it impacts locally and globally in terms of environmental impacts and what can be done to improve the conditions or improve the situation. in this case, we have different options, or there are different outcomes for life cycle assessment. You can either go for material substitution, you can go for technology advancement. So unless we know the gravity of all these things, we cannot do anything else further to improve the situation. So that is the ultimate goal of life cycle assessment. So LCA studies which we have conducted so far, we have just mentioned a few. Out of critical materials, I'll just go through lithium, and out of the energy systems, we have all the major electricity generating technologies, and we have looked into almost all the life cycle phases. So for the lithium supply chain, we have looked into, of course, nickel, cobalt, and lithium. So here we have mentioning only lithium. So this is a basic flow chart where we have done the life cycle assessment of the lithium supply chain, and we have considered the scenarios where conventional routes is considered to be the base case, but Chile-China route, where Chile is the brine, both of them are the brine routes, the conventional brine routes for both lithium iron phosphate, that is LFP battery, and nickel cadmium aluminum, that is, nickel cobalt aluminum NCA batteries. So those red highlighted ones are the base cases. And we have compared the environmental impacts with other 3 scenarios for both types of batteries. And these 2 are advanced lithium supply chain routes, which are yet under research. So we have considered geothermal brine as well as oil field brine, both assuming in-house development of both the batteries. So we do environmental assessment, we do energy assessment. Energy assessment is a subset of environmental assessment, where we get the energy demand. And as a result of life cycle assessment, we get all the major environmental indicators. And we have added multi-criteria decision making so that we can prioritize the environmental impacts and decide upon one sustainable lithium supply chain from among the choices. So that is purely dependent upon what do you want to do or what do you want to prioritize. Okay. So next, moving on to the different generation options. We have conducted studies on CCGT, that is combined cycle gas turbine, which is natural gas fired, and CCGT with CCS, that is carbon capture and storage, nuclear, coal generation, wind plus storage, solar and solar plus storage. So our base cases, 500 megawatt capacity of CCGT, which generates 3 terawatt hour per year. Okay, so yeah, so these were the electricity generating options which were compared on the basis of LCA. Next one is dispatch modeling for system optimization. So this is the second part, actually, the reliable electricity, where we try to model the system, model the entire grid, so that the system is working under optimum conditions and at the same time offering less cost and providing reliable electricity to the consumers. So these are the different load zones which we have considered, and this is the transmission lines which include 345 kV and 150 kV of the ERCOT grid. So why do we do grid dispatch modeling? As mentioned, we can test future scenarios, prospective scenarios. We can extend the current scenarios. There are different options of doing it. And we can understand. So the ultimate aim of grid dispatch models is to generate the marginal cost and, of course, the technical implications. We'll see a little bit in detail in the later slides. And we can see how the solar and wind generation impacts the entire electricity grid, how we can minimize the congestion, transmission congestion, how the environmental impacts are there when you build or when you run, when you build new facilities, when you retire new facilities, or you run the different scenarios. And of course, how the intermittent generation or the dispatchable generation impacts the entire environmental scenario of the grid. So these are the common aims of doing grid dispatch modeling. So this is the platform which we did grid dispatch modeling. It's called Aurora, which is a software which is by software from Energy Exemplar. So this gives a general overview of how the software works. These are the inputs, the prices, demand, resources, the weather pattern, the capacity, and these are the outputs we get from the model. So there are 2 aspects of the model. You can either use prediction cost modeling, where you just use the existing scenarios, or you can also go for long-term capacity expansion modeling. So the advantage of Aurora is that the data is on a nodal basis. or the granularities on the nodal level so that we get more exact and accurate outputs on a lower granularity. So this is the theory behind the grid dispatch modeling. You have economic dispatch and unit commitment both coming together in Aurora. In economic dispatch, you assure reliable electricity by minimizing the generating cost. Of course, it is dispatching economically. And unit commitment means the deciding upon which are the optimal combination of the different generators to provide electricity at each amount of time in such a way that it meets the demand. And of course, you cannot do it without any limits. You have constraints. It is an optimization model where it works on the constraints related to the power balance equation, which means at every point of time, the generation should meet the demand. And each generator has its operating limits, and the transmission line has also its own constraints. So these are the predicted outputs. You can see how the generation portfolio is based on the demand. You can understand the capacity factors. You can understand the generation mix, how much renewable generation is curtailed. Curtailment means even though you have a capacity for the renewable generation, it's not properly utilized due to transmission congestion. That is curtailment. And some of the load may be unserved. So how much hours are unserved? What is the cost of electricity at that time? And of course, the final goal, the environmental impacts of the predicted generation. So these are the three generation scenarios which we have considered. The base case is our current trend scenario where we have 30% of wind, 17% of solar, and 44% of CCGT and 5% of nuclear. So this is the base case which is predicted up to 2050. And this is a second scenario. This generation mix is for 2050. So for the second scenario, we have reduced a little bit of, the renewable generation is more. That's why it's called the high solar wind scenario, while reducing the CCGT and keeping the nuclear the same. And the third scenario was we have reduced the renewable a little bit and increased the CCGT as well as nuclear. So we have considered these three different scenarios for our analysis. And the last point is, of course, affordable electricity. For affordable electricity, you need to find out what is the cost of electricity. So this is phase 3 of our project. So we consider when we just say cost of electricity, we know the term levelized cost of electricity. The definition for levelized cost of electricity is how much energy is consumed in how much time, and what is the cost of 1 unit of electricity. So that purely depends upon your consumption of electricity. But in our case, we are trying to find out a new metric, which is called the consumer cost of electricity, which not only depends upon your usage, but also it depends upon your installation cost, which is called the capex, or the construction and installation cost, considering the lifetime of the product as well as the discount rate. Then you have the OPEX, which is the operating cost, which considers the replacement cost, the O&M cost, and the fuel cost. And of course, for renewable generation, you don't have any fuel cost. So these two things add up, and you want to annualize it. You use the lifetime as well as the discount rate. And you have the total electricity that is produced from the system. And when you bring in other parameters like congestion cost, that is the transmission line congestion due to the usage of electricity on the other side and the generation of electricity on this side, mostly from the renewables. So the transmission lines will be congested and they will incur a cost. So that is called congestion cost. And the other parameter which we are considering is the environmental cost due to the environmental impacts offered by the total electricity generating system. So we are trying to deduce a new metric, which is called the consumer cost of electricity, including all these externalities. So these are the two externalities which we are trying to include as part of our analysis. And this part is done by our economist, George. So I'll just quickly take you through some of our results, starting from phase 1. So these are some of the results which we have for the life cycle assessment of the lithium supply chain. If you remember, we have considered 4 different scenarios for 2 types of batteries of the lithium supply chain. So I have just shown the comparison of the environmental impacts based on the base case. The base case is Chile-US route, and these differences or these bar graphs show the percentage change from the base case. So of course, negative numbers show the decrease in impact and positive numbers show the increase in impact. So these are the 15 environmental impacts which we consider for our analysis. Out of which GWP is common, you know, it's global warming potential, land occupation, water consumption is WC. So these are the, and we have other ecotoxicity, eutrophication and other impacts also considered. So we can see that when it comes to GWP, the base case has the highest GWP because the 3 bars are coming down, showing that the other scenarios have less global warming potential compared to the base case. Similarly, for the NCA battery, a similar analysis has been done and the results are presented. Other aspect of LCA which we have conducted is the environmental impacts of the generating technologies. And here the base case is the CCGT, the combined cycle gas turbine, which is natural gas fired or fossil fuel fired. A similar analysis on this basis. We have compared these 5 different electricity generating options to the CCGT. CCGT plus CCS, which is a carbon capture and storage. The wind, solar, PV, you know, both are renewable energy sources, and BESS is battery energy storage system. You know, wind and solar energy sources are renewable sources and they need storage because they are intermittent. And solar energy is available only during the morning hours. And if you want solar energy to supply during the sunshine hours, you need battery storage. So when you can see that storage, when for both wind and solar energy sources, you need storage also. So we have analyzed that as 2 different separate scenarios. So we have finally come under the conclusion that when storage increases or when we bring in storage to the renewables, it increases the environmental impacts. Of course, it is understandable because you have to put in batteries. But there is a trade-off between reliability and clean aspect of energy. You want reliable energy, but in that case, the battery energy storage system needs to be added, which increases the environmental impacts. So in this case also, comparing to the CCGT, just for an example, the global warming potential is the global warming potential increases for all other global warming potential decreases for all other electricity generating sources compared to the base case, which is CCGT. And we have given select environmental impacts as an example. So here in this case, one interesting fact is the global warming potential. This graph, you can see that when carbon capture and storage is added to CCGT, hope you know what is carbon capture and storage. You capture all the carbon that is emitted from the CCGT and store it somewhere. So that is a way of reducing global warming potential or greenhouse gases that is emitted to the atmosphere. So when we compare the 4 different major environmental impacts, one interesting fact is that CCGT plus CCS, which is a green bar, has less global warming potential in comparison with CCGT. But you can see that all other impacts increase for the CCGT plus CCS combination. This is because CCS system has to be built, it has to be operated, all these things are there. So its major advantage is reduction in global warming potential because it captures the operating emissions and stores it in distant locations so that it acts as a storage for carbon. So these are some of the major impacts. Of course, we have reduced all the 15 environmental impacts, but I've shown only some major ones with its own per megawatt. That is for 1 megawatt of electricity that is generated. So these are some of the timelines just to get a sense of how the environmental impacts are. For the cumulative variation means it's added each time in every year. So 30 stands for the years of operation. So here you can see that as the year goes on, the CCGT emissions, the CO2 emissions increase. For CCS, it's a little bit less. And but for the other emissions, but for the other electricity generating technologies, that is the wind, solar, and the battery storage technologies coming together with the renewables, you can see that there is an increase during the beginning, and then it keeps on constant because the operating emissions during the operation of the renewable energy technologies, you don't have any additional GWP emitted. In this case, you can find the per megawatt variation. That is, as the generation increases, I divide it by the total electricity generated. In this case, these remain constant, but the renewable energy technologies and the batteries together with it has a sharp decline in the global warming potential as time moves on. Similarly, for water consumption has a similar pattern, but in this case, there is a major difference. For CCS, CCGT plus CCS, the graph is above the CCGT graph because for the operation of the CCS plant, you need water. So that is something which is interesting. So some of the general observations are the trade-offs among technologies are apparent. You can find for each type of, as we have seen, the characteristics of the different environmental impacts having the different electricity generating technologies are different. You cannot say that one technology is better than the other in terms of all the environmental impacts. So every technology has its own higher impacts, its own lower impacts, and most of them are spaced unevenly. You cannot say that all the impacts are available locally or they are affecting globally or anything like that. There cannot be a general statement on all these things. And when you build a new capacity, mostly the front-end loading of impacts is more, which means the CapEx. E-CapEx stands for environmental CapEx. That is, the environmental impacts during the construction is more. But in most cases, or for some impacts, you can see that the operating impacts will override the increase in the front-end loading of impacts. So that is also possible, but sometimes it will not occur. So all these depends upon the generating technology characteristics, its materials, where it comes from, where it is manufactured, where it is operating, where it is being recycled. All these depends upon specifically the characteristics of the generating technology. So next, moving on to the transition scenarios. So these are the impacts. As I have already mentioned, we have looked into two different scenarios, mainly two different scenarios. The first one, which is the base case, and the second one is the high renewable scenario. And here we can see that the global warming potential, the variation of global warming potential from 2023 to 2050 for the different life cycle phases of each generating technology. So the CCGT OPEX, it goes on decreasing because it's in comparison with the difference between the high renewable scenario and the base. So when it comes to water consumption, you can see that many plants are added, many plants are retired. So all these depends upon the various numbers which we have deduced based on the characteristics of the different electricity generating technologies. So in this case, the cost, when we look into the cost, we can see that when there is a high renewable scenario, this is also S2 minus S1, where S2 is the high renewable scenario and S1 is the base case. We can see that the congestion cost increases. The difference increases between the two scenarios, that is S2 minus S1, and the cost is represented in $1 billion. So as we know, when renewables are inducted into a system, the transmission should be equipped in such a way that the transmission line should be able to cope up with the extra punching in of the renewable energy. But at the same time, the dispatch model will try to balance supply and demand at every instant of time. But in this case, when there are more renewables in the system, of course, the transmission line congestion is more, which causes more congestion cost. So that is why these blue lines are more, and the difference between the two scenarios in 2050, this is the year 2050, is more. So when we try to include the externality cost also, we can see that the GWP is more. The difference, the GWP impacts are more when we compare the S2 and S1 cost. But here in this case, we consider the all the environmental costs also, which means the total cost is the sum of all the costs of the externalities as well as the operating cost. Yeah, so some of the general observations for this is When we try to integrate more solar and wind, it increases the congestion cost and curtailment. Curtailment, I have already mentioned. Curtailment means even though there is more supply of energy, it cannot be effectively utilized on the other side due to infrastructure deficiency in transmission lines and capacity. So that is something which increases the congestion cost. So it's not always good to say that you have to pump in more and more renewables. You should have additional storage, and at the same time, the infrastructure and transmission line should also be in such a way that it can be the extra renewable pumping can be managed on the other side. And some costs are, of course, increase. Some externality costs like environmental cost will increase, but others will decrease. Of course, will depend upon the generation portfolio, the mixed portfolio, which we are trying to analyze. And others decline. Some costs increase, some costs decrease with externality cost. And at all points of time, it may not be sufficient to cover the direct cost, which the consumer has to pay. So Texas consumers, they pay high electricity cost, and there is some possibility of environmental degradation. They do not benefit from all the environmental improvements because when we study environmental costs or externality cost, we should look into the environmental cost on a region to region basis. So these cost of externalities need to be defined or need to be studied on a localized basis. Then, and as we all know, the largest benefit is always from the reduction of greenhouse gas emissions, but they are not localized as far as studies are concerned. Yeah, so this is the last portion or the to be done portion of our project, where we are trying to replace the levelized cost of electricity. LCOE is the levelized cost of electricity, which is a common metric, which is used to define the amount you have to pay when you consume 1 megawatt hour or 1 kilowatt hour, whatever is the unit of electricity. So what we are trying to do is we are trying to replace LCOE with a more comprehensive metric, which includes the costs of externalities, as I have already mentioned, including the integration cost, the congestion cost, and the environmental cost. So the major challenge in that case is we have to identify or we have to reduce the externality cost for all the LCA impact categories, and they need to be localized also, which means it is specific for a study region or a study area. So that also needs to be understood. So these are some of the preliminary results which are from literature, and still we have some numbers over here, but we are trying to deduce more accurate numbers upon research from the, of course, results from the LCA studies which we have done and the grid dispatch modeling studies which we have done, and all these two funnel to the final amount of money which you have to pay. So moving on to the overview of our project, we know that all from the studies which we have done, we know that every energy system, even if it is a renewable energy system, even if it is a non-renewable energy system, you have different types of environmental impacts at the different life cycle phases, starting from the scratch or from the cradle to the end of life or the recycle. So we cannot say that no energy system is free from environmental impacts, even if it's a renewable source. Then LCA studies, what they do is they isolate where does the impact come from, or when are the impacts occurring in what is the life cycle phase. It can be during the sourcing, processing, manufacturing, or operations, or end of life, and how you can improve the performance of each phase if you know at which point the impacts are more prominent. What impact is prominent at which phase? So we can compare the individual generating units, we can compare individual electricity generating options, we can compare different materials, we can study different options and come up with more improved ways of developing the same thing by reducing the environmental impacts. And you can optimize reliability and environmental impact and consumer cost, as I told in the beginning. So environmental load from solar and wind technologies are front loaded. Front loaded means it's mostly during the construction phase, but during the operational phase, they don't have much of the impacts. And they are mostly local. And yeah, so we need to carefully establish which impacts are important, where, when, all these things. So we will look into a comprehensive approach wherein we'll be adding environmental cost. So these are some of the publications which we have from our project. We have published LCA studies on the cobalt supply chain and on the electricity generating technologies. And on the lithium supply chain, it's in the making. And we are planning to submit for a conference also on the grid dispatch modeling work. And we have also presented at the GSC Connects 2023 our studies. Yeah. So these are our current and past members of our project, and express our sincere gratitude to all those who are involved, including the students. Thank you. Question?
Becky's hand shut straight up, so I'm gonna go there first.
Very good presentation. You've done a lot of work, obviously. And I'm just, I'm really curious about the gas generation plus CCS and why that consumes so much water. Does it, is it, just go ahead. You can answer generally. I have questions.
Yeah, CCS, carbon capture and storage, is an additional infrastructure you add to the combined cycle gas turbine. And it is an external facility or an infrastructure which needs its own capex and operating characteristics. And what it does, it catches the operating emissions. It catches what do you say? It just stores the operating emissions from the CCGT, and it transports it through a long pipeline, and it stores in a saline aquifer or somewhere, something which is distant apart from the CCGT. So when we take the entire life cycle analysis of a CCGT in comparison with a CCGT plus CCS system, only the global warming potentials are less, but it has all the implications of an external infrastructure or a facility being added and its operation based on natural gas. So that's why the water consumption is also a part of the operating characteristics of the CCS.
What is it that takes the water other than the capex? I mean, so I guess I'm not clear because there are different methods of CO2 capture that can be used. So I'm just, it just seemed like it was a huge increase in water consumption.
Yes.
I wonder, is it, could it be from having to drill wells?
Yes, it includes, of course. The
water cooling.
Yeah, the cooling is
right
there. Cooling is a major part. And if we are starting from scratch, of course, the production or the material manufacturing also has its own part. So I need a very long pipeline for the transportation. It's not only the operation of the CCS, it starts from scratch. So all the parameters which come, or all the materials which are used for the production of that facility will contribute to the water consumption, and of course cooling for the operation of the CCS plant.
Okay, thank you.
Thank you. Anybody else online or in person with a question? I have one loaded, but I always try to give priority first. Okay, well, I'll ask my question. So I was just kind of curious, when you are building the scenarios that you consider in your life cycle assessments, like, what goes into those scenario selections? How do you build those scenarios? What parameters are you thinking about when you choose this scenario versus that scenario to do those analyses?
It's for scenario selection, you can select any scenario based on your what you want. So the major or the first thing that comes to your mind when you select a scenario is you want a scenario which has more renewables into it and you have less renewables into it. And we have, of course, some studies which are published by ERCOT LTSA, where they have themselves defined some scenarios where in the future you bring in more renewables. what will be the demand, what will be the capacities of the solar and wind plants in another 30 years frame. So we have already a baseline on that. We take that as well as we make some small adjustments so that our requirements like what will happen if this much of solar is added, what will happen if this much of wind is added. And we need that much of battery also to compensate. So the scenarios are to some extent defined, customized, but we of course refer to the LTSA reports also, which are published by ERCOT, which is the baseline. Which we look at.
Okay. So if I've understood you correctly, then what you're saying is you look at some potential projections or estimates.
Yes.
Like ERCOT as
Yes.
kind of the core
Yes,
of this.
yes, yes.
Okay, right.
We can also look into a nuclear heavy scenario. Such things are also possible. Whatever we want, we can of course customize our scenarios based on our studies which are already there.
Okay. Well, again, I always. Let's see, checking online, don't see anything online. Nope, haven't seen one. Okay, well, I'll ask another question. There was a lot to absorb, but on a couple of those charts, it looked like, when you start stacking all of the different impacts,
Mm.
I couldn't help but notice, it seemed like, maybe I misread it, but it seemed like nuclear was just the way to go, right? Because it seemed like on several of those charts, nuclear had like nothing, right? Whereas all of the other options, solar, wind, combined cycle gas, with or without CCS, like they all had these sort of stacked add-on, land use, et cetera, et cetera, et cetera. So did I see that correctly? I mean, should we all invest in nuclear? Is that like a key takeaway or no?
Yeah, for the first two scenarios, which I showed the charts, we are not building any nuclear power plants. So building a nuclear power plant has its own constructional or the capex front, capex environmental impacts. But our scenarios assume that in the first scenario, S2 and S1, no nuclear power plants are being built.
Okay, I misunderstood.
Yes.
Yeah.
So if we have nuclear power plants built, we have already done the life cycle assessment of nuclear power plants. We have the per megawatt numbers also. It is significant, especially the ionization radiation potential is more when during the operation of the nuclear power plant. And yeah,
Yeah,
of
no, I
course.
just misunderstood it. Apparently it was saying no new nuclear, so that's fine. Becky's got another one.
Do we really know the cost of disposing radioactive waste from nuclear power plants now? I mean, other countries are doing it, but the US is not. But so are those numbers out there for disposal of the waste?
That question I'm not sure how to answer because
It's I'm just throwing out an idea. It's something that we're sorely lacking in this country. And
yeah, it's environmental impacts. Yeah, yes. Yeah, nuclear waste. Cost means you're mentioning about the environmental cost or the
I'm just talking about the dollar amount, what it's going to cost us in dollars to establish facilities to dispose of our waste, like they're doing in France and Switzerland. And anyway, just curious.
Yeah, that's what actually phase 3 is focused on. If I'm answering it correctly, maybe. Yeah. The phase 3 is something wherein we deduce the environmental cost of each electricity rating technology. Environmental cost is actually what you are telling. How much cost will be incurred by the consumer so that it mitigates the specific environmental impact that is produced by that technology. I have a generation mix and I have an electricity that's produced from that generation mix. I'm using it, but how much should I pay so that those environmental impacts are nullified or neutralized? So that is the phase 3 of our project, wherein we try to localize it specific to the region of study, and that is added to the consumer cost of the cost of electricity, so that we get an aggregate number. That's what I'm
So also as a kind of riff on that, we probably have a pretty good idea of what the economic cost is going to be to dispose of waste. Part of Energy spent many billions of dollars essentially characterizing the amount. And that was, well, it's not a bad place. It's a good place. My opinion. I mean, sending it out to Nevada test site is not bad. It's much better than keeping it in swimming pools all over the country. That being said, I mean, there's probably very little information on end of life options for nuclear, where you're looking at, we just don't know. It's a study that could be done. My sense is from a risk standpoint and an economic standpoint, it's going to be much less it's going to be much less than in a sense. I mean, especially if it's isolated. And there's ways to do it. We could reprocess. There's a lot of things we could do, but in the end, you know, it has a very high capacity factor. So its plants are running all the time. And they're generating no CO2. It uses water for cooling, but there's a little bit of that, a little bit of land, and some land to do the mining to get the uranium process.
Clear makes probably the most sense in the long term. I did do my master's thesis on an analog to Yucca Mountain, and there are a lot of problems with putting it there.
Okay. It may be, but I think that we can engineer our way out of it. That's my opinion.
Well, I have, if you'll permit me, I have one, what I hope is kind of a fun last question, right? So you understand all of these assessments and the impacts like better than I personally could probably ever do, right? So my question for you is, given those three kind of factors that we want to think about, right? Reliability, environmental impact, and cost, based on just this synthesis of all this work that you're seeing, if you were energy emperor, right, what would you say should be the energy mix that we should be shooting?
An optimum combination, which gives us a trade-off, a reasonable trade-off between these three. Definitely, if I go for reducing the cost, then I may have to compromise on environmental.
Sure, but what I'm asking is to optimally balance those three, do you have a sense of what the energy production mix looks like? I mean, is it mostly solar, mostly nuclear, and mostly, combined cycle gas? Do you just synthesizing everything that you've seen, have a feeling for what the optimum mix of generation options looks like or might look like?
Definitely, on an environmental perspective, you need renewables, but for reliability, I have to bring in batteries with renewables, which again it increases environmental impacts. And of course, batteries increase the cost. So to have a clear answer, maybe it's a matter of what we say. We have to work more on it, or we may have to do sensitivity on different generation mixes and finally arrive at an optimal combination. I would never say that leading more towards renewables will bring in the desirable impact. We should have both in an optimum way. We cannot always, in my personal opinion, renewables of course has its own environmental impacts, positives in that way, but it has negatives also, even if in terms of environmental impacts, because I have to bring in storage and I have to.
It kind of gets into a policy question, right? What's most important to you? Cost, environment, reliability, or how do you weight them? Right? So yeah, it's interesting. Okay. Well, one last one. Yeah, we got a few more minutes. Time.
There may be one combination that makes the most sense now, but maybe we should be working towards alternate combinations, like working towards nuclear. All the things we need to.
Yeah, it definitely depends upon the demand. Yeah, what type of demand, especially if you are bringing in more electric vehicles, it's a specific. It can be localized.
Yeah, the other aspect of this that's really unknown is the demand. And so we're looking at the expectation is a 50 gigawatt increase in demand in the next 5 years, which is almost a 50%. So it's a huge number that's going to require basically to supply the electricity. So you're right. I mean, the grid that we have today is servicing Texas, does it pretty well. It's it's somewhat fragile during extreme events, but it works pretty well and it's pretty inexpensive. The challenge is when we have really, really large increases in demand. And we're not exactly sure how you have to deal with that. My sense is that a combination of like 50% base load and 50% renewable that's firmed up with batteries will work. But a lot of it's on the demand side.
Hey, well, thanks again, everybody, and we'll see you. I think we have a seminar next week, right? Yep. We'll see you next week for the next Bureau Summit.
Thank you.